Welcome to the deep dive. Today, we're tackling something really fundamental, symmetry in the universe.
Yeah, it sounds maybe a bit abstract, but it's everywhere.
Right. It's not just about, pretty patterns. These underlying symmetries, they dictate everything from how a ball flies through the air to, well, the existence of particles we can't even see.
Exactly. Think about just looking around the fact that the laws of physics seem to be the same no matter which way you're facing. That's isotropy, a key symmetry.
And it operates behind the scenes, often totally unnoticed, but it's shaping how everything
They
works.
are the deep rules. Absolutely.
And you, our listener, pointed us towards one specific, really fascinating symmetry, the mirror image, the difference or lack thereof between left and right. Physicists call it parity.
It seems so obvious, doesn't it? Like, of course, a mirror image is just a mirror image.
That's what you'd think. But hold on, because this apparently simple idea led to a massive shakeup in physics, we're going to trace this whole story.
From the initial ideas about symmetry through what everyone thought they knew about parity.
To this really bizarre puzzle that topped up, and then the experiments that just completely flipped the script.
And yeah, the listener material, especially citing C.N. Yang's Nobel lecture, gives us a great pathway through this.
So our mission today: understand why symmetry is so crucial in physics, follow the twists and turns of how scientists started questioning something like left-right symmetry, and really get a handle on the huge implications when they found out it isn't always conserved.
Okay, let's dive in. First off, why this big focus on symmetry in physics? Why is it so important?
Good question. Where does this obsession come from?
Well, symmetry laws are fundamental because they show us the underlying order, the constants in the universe, what stays the same even when other things change.
Like you mentioned, isotropy space looking the same in all directions, and homogeneity it being the same everywhere.
Right. Those aren't just nice thoughts, they're foundational symmetries. Even early scientists had an intuitive sense of these consistencies.
And they're not just philosophical points, are they? They have real, measurable consequences.
Absolutely. Take Galilean transformations. The idea that the laws of physics are identical whether you're standing still or cruising at a constant velocity.
Like me on a really smooth train ride.
Exactly. You can't really tell you're moving, physics-wise. That was basic to Newton's mechanics. And Yang even mentions things like the number of elastic constants in a material being tied to spatial symmetry.
Okay, but here's where it gets really, really interesting for me, this deep link between symmetries and conservation laws.
Ah, yes. This is truly profound. We now understand there's a direct correspondence. For every fundamental symmetry, there's a conserved quantity.
Like what? Give us an example.
Okay, so the fact that physical laws don't change if you just shift everything in space slightly, that symmetry gives you conservation of momentum.
Wow.
And the fact that laws don't change if you rotate things, that gives you conservation of angular momentum. It's like a hidden code.
That's incredible. Things I learned separately in physics class symmetry, conservation laws are actually like two sides of the same coin.
Precisely. And as Yang notes, this deep connection, this mathematical link, wasn't fully grasped until, well, relatively recently, the 20th century.
So the conservation laws themselves were known earlier, but not why they were connected to symmetry.
That's a good way to put it. The deep theoretical underpinning, linking them to symmetry, became much clearer over time.
And then relativity came along and sort of turbocharged this whole idea.
It did. Both special and general relativity really weave symmetry principles into the very fabric of the dynamic laws. It's not just that the laws happen to have symmetries. The symmetries are more fundamental, more integrated.
And relativity introduced new symmetries, things that weren't obvious.
Yes, exactly. Symmetries that often needed really complex, high-precision experiments to even confirm they existed.
Which must be incredibly validating for physicists, right? Finding this deep, elegant order emerging from all the messy experimental data.
Oh, absolutely. It fuels the belief that nature operates on these beautiful, simple principles, even if uncovering them is hard work. It suggests we're on the right path.
But the story didn't end there. Quantum mechanics, that really embraced symmetry too, didn't it?
Embraced it? I would say symmetry is almost the language of quantum mechanics. The quantum numbers we use to describe particles and systems, they often directly represent the symmetries of that system. It's absolutely central.
Can you give us some examples in the quantum world?
Sure. Think about the periodic table of elements. Its structure, the way elements in the same column behave similarly chemically, that stems directly from the isotropy of the electromagnetic force. The Coulomb force only cares about distance, not direction.
Okay, that makes sense.
Or, even more dramatically, the prediction of antiparticles, things like the positron, the antiproton. Their existence was predicted theoretically before they were found, based on the symmetries required by Einstein's special relativity, specifically Lorentz transformations.
So the maths, the symmetry principles, actually told physicists to go looking for these completely new kinds of particles.
Exactly. It's a stunning example of how trusting these underlying symmetries can lead to profound physical discoveries. The mathematical elegance leads to real, tangible consequences.
Okay, so let's zoom in now on our main focus. This left-right symmetry parity, it feels so basic.
It really does. People have wondered for ages if nature inherently tells left from right. Philosophers debated it.
And obviously, in daily life, left and right are different. My heart's on the left, mostly. Screws turn one way.
Right. And even language sometimes reflects this, like right being good or correct. But in physics, parity is about something more fundamental. In quantum mechanics, we assign it a value. +1 for even parity, -1 for odd. It describes how a system's wave function behaves if you flip the spatial coordinates, like looking in a mirror.
But the standard thinking in physics for a long time was that these everyday differences, heart placement, etc., were just accidents of history or
Right.
biology, not baked into the fundamental laws.
That was precisely the assumption. The laws themselves were thought to be perfectly mirror symmetric. The classic thought experiment is the mirror image man.
Ah, yes. If you had someone who was a perfect mirror image inside and out, eating mirror image food.
The laws of physics should treat them exactly the same as us. They should function perfectly fine. That encapsulated the classical view of parity symmetry.
So in classical physics, parity was recognized, but maybe not seen as quite as crucial as something like rotational symmetry. Why was that?
Well, mainly because it's a discrete symmetry. It's an either flip, left or right. Rotational symmetry is continuous. You can rotate by any tiny angle.
And that distinction matters mathematically.
In classical mechanics, yes. Continuous symmetries were known to directly lead to conservation laws,
Yeah.
like we discussed with momentum and angular momentum. Discrete symmetries, like parity, generally didn't have that direct link classically.
Okay, I see. Different kind of symmetry, different classical implications. But then quantum mechanics arrived and sort of changed the game again.
It really did. Quantum mechanics blurred some of those classical distinctions. And importantly, the law of right-left symmetry, parity, did become associated with the conservation law, the conservation of parity.
And how did that idea become established? It wasn't just assumed, right?
No, it emerged from observations in theory. Yang points to Otto Laporte's work back in 1924. He was looking at electron energy levels in atoms.
Okay.
He noticed they could be neatly classified into two groups, which he called even and odd. We now know this corresponds to parity +1 and a -1.
And he found a rule about them.
Yes, a selection rule. When an atom absorbed or emitted a photon, a particle of light, its state always jumped from an even level to an odd one, or from odd to even. It never went even to even or odd to odd in those transitions.
So the parity had to flip. That strongly suggests something is being conserved overall, doesn't it?
Exactly. It implicitly suggested that the total parity of the system, the atom plus the photon, wasn't changing. The photon itself carries parity.
Even if Laporte didn't call it parity conservation explicitly back then?
Right. Then, a few years later, in 1927, Eugene Wigner provided the theoretical proof. He showed that Laporte's observed rule was a direct mathematical consequence of the reflection invariance, the left-right symmetry of the electromagnetic forces governing the atom.
Ah, so Wigner connected the observation to the underlying symmetry. That's key.
Absolutely. It cemented the idea. And because electromagnetism is so fundamental, and parity conservation held so well there.
It seemed natural to assume it held for other forces, too, like the nuclear forces they were starting to understand.
Precisely. As physicists explored nuclear reactions, discovered new particles like mesons, and grappled with those weird, strange particles.
Strange particles.
Yeah, particles that were produced easily but decayed surprisingly slowly.
Yeah.
Anyway, in all these new areas, parity and its conservation became a standard tool. They'd talk about the intrinsic parity of a nucleus or a pion.
So it was a really useful concept, helping make sense of experiments.
Extremely useful. Its success built up a lot of confidence, maybe even overconfidence, in the universal validity of right-left symmetry.
Okay, so parity conservation is looking solid, but then trouble starts brewing. This puzzle emerges in the early 1950s. What was that all about?
Right, this is where the cracks start to show. To get it, we need to remember the fundamental forces.
Okay, quick recap.
You've got the strong nuclear force holding atomic nuclei together, electromagnetism dealing with charge and light, the weak nuclear force responsible for things like beta decay, where a neutron turns into a proton and certain particle decays, and then gravity, which is negligible here.
Got it. Strong, EM, weak, gravity. And this puzzle involved. Which ones?
The puzzle itself involved particles called K-mesons, specifically two types initially thought to be different, named theta, tau, and tau. They decay via the weak force.
Okay, theta and tau. What was puzzling about them?
Well, in 1953, Ballitz and Fabry realized that by looking closely at how they decayed, you could figure out their intrinsic parity.
How they broke down into other particles.
Exactly. The theta meson was seen decaying into two pions. Now, pion has odd parity, medically 1 if you have two of them, and parity is conserved in the decay.
Then odd times odd gives even. So the theta should have even parity, +1.
That was the logic, yes.
That's
It's a bit more complex involving their relative motion, but that's the gist. The tau meson, meanwhile, decayed into 3 pions.
Okay, so odd times odd. That's odd. So the tau should have odd parity, -1.
Correct. That's what the decay mode strongly suggested. And by spring 1956, detailed experimental studies of the pion distributions seemed to confirm it. Theta appeared to be even parity. Tau appeared to be odd parity. Different particles.
Problem solved then. Two different particles, different decays, different parities.
Ah, but here's the kicker. Other experiments measuring their basic properties kept showing that the theta and the tau had, within experimental error, exactly the same mass and exactly the same lifetime.
Wait, how can that be? If they have different parities, shouldn't they be fundamentally different particles with different masses and lifetimes?
That was the huge contradiction, especially for particles that feel the strong force like these K-mesons were thought to. The expectation was clear. Different spin, different parity should mean different mass, different lifetime. Identical mass and lifetime strongly implied they were actually the same particle.
So one set of experiments says they must be different particles because of parity, and another set says they must be the same particle because of mass and lifetime. That's a puzzle.
It was deeply perplexing. Yang actually quoted himself from a 1956 conference report, basically saying, look, the decay data points to them being different, but the mass and lifetime data is so compellingly identical, we have to keep an open mind. You can feel the frustration.
It's like the universe was sending completely contradictory messages. Two puzzle pieces that just wouldn't fit.
Precisely. It was a major crisis brewing in particle physics.
And the solution when it came was absolutely radical, wasn't it? It meant throwing out parity conservation itself, at least in some situations.
Exactly. The breakthrough came from Sungdao Li and Chen Ning Yang. They decided to systematically go back and check the foundations.
What did they find?
In mid-1956, after scrutinizing all the past experimental evidence, they reached two startling conclusions. First, unbelievably, no previous experiment involving the weak interaction had actually been designed in a way that tested parity conservation directly.
Really? They just assumed it held?
Essentially, yes, or rather, the experiments simply weren't set up to see if a process and its mirror image behave differently. Second conclusion. While experiments involving strong and electromagnetic forces showed parity was conserved to very high accuracy.
The accuracy wasn't quite high enough to rule out the possibility that the much weaker weak force might violate it.
Precisely. There was just enough wiggle room. It was a stunning realization. Maybe a fundamental symmetry of space-time itself wasn't absolute.
That must have felt almost heretical, questioning something so basic.
Oh, it was. Li and Yang themselves said they were driven to it through frustration. They'd tried everything else to solve the theta-tau puzzle. It wasn't their preferred explanation initially.
Because physicists were used to symmetry as sometimes being approximate, right? Like isotopic spin, which holds for the strong force but not electromagnetism.
Exactly. But those were considered internal symmetries. Space-time symmetries, like rotations or parity, were thought to be exact, inviolable. To suggest one of those could be broken, even just by the weak force, was a huge conceptual leap.
And it even made them wonder if maybe our usual ideas about space and time break down at these very small scales involved in weak interactions.
It definitely opened up that kind of speculation. If parity fails, what else might be different down there?
So if the weak force was violating parity all along, why didn't earlier experiments, like studies of beta decay, show it?
Good question. Two main reasons Li and Yang pointed out. First, the neutrino involved in beta decay. It has almost zero mass. That tiny mass creates ambiguity in how you interpret the energy spectrum of the electrons emitted in beta decay. It basically muddies the waters, preventing you from indirectly deducing parity information just from the spectrum shape.
So the neutrino's properties masked the effect.
In those simpler experiments, yes. But the second, bigger reason was that nobody had done the right kind of experiment. To directly test parity, you need to compare a process with its literal mirror image.
Like set up an experiment and then set up its reflection.
Essentially, yes. You need to look for an asymmetry. Does the experiment behave differently from its reflection? Previous beta decay studies measured things like energy, but they weren't designed to look for this specific left-right asymmetry in the overall process.
So Li and Yang realized this gap and said, okay, here's how you could test it.
Exactly. In the summer of '56, they proposed specific experiments involving beta decay and also decays of other strange particles, explicitly designed to look for parity violation.
What was the core idea?
The principle was clean. Set up an experiment involving a weak interaction. Then imagine or actually set up its mirror image. Compare the results what your detectors measure. If the readings are different between the experiment and its reflection, then bang!
Yeah.
Right-left symmetry is broken for that interaction.
And the most famous, the definitive test, was the cobalt-60 experiment led by Chen Wu.
Yes, a landmark experiment. Conducted late '56, early '57 by Wu, working with Ambler, Hayward, Hopps, and Hudson at the National Bureau of Standards. It was incredibly clever, but also technically very demanding.
What did they do?
They took radioactive cobalt-60 nuclei, and they cooled them down to extremely low temperatures, just a fraction of a degree above absolute zero,
Why so cold?
to minimize the random thermal jiggling. At those temperatures, they could use a magnetic field to line up the intrinsic spins of most of the cobalt nuclei, so they were all pointing in the same direction.
Okay, so they have aligned nuclei, decaying via beta decay, a weak interaction. Then what?
Then they measured where the electrons, the beta particles, came out, relative to the direction the nuclei were spinning.
And the key was comparing this to the mirror image.
Precisely. If parity was conserved, the electron should have come out equally often up and down relative to the nuclear spin direction. The mirror image would look statistically identical.
But that's not what they found.
Not at all. They found a huge asymmetry. Significantly more electrons were emitted in the direction opposite to the nuclear spin and in the same direction. The experiment did not look the same as its reflection.
Wow. So clear, undeniable proof right there in the data.
Undeniable. It was definitive evidence that parity conservation is violated, broken by the weak interaction responsible for beta decay.
That must have sent shockwaves through the physics community. And Yang really emphasizes the skill involved merging tricky beta decay measurements with that cutting-edge, low-temperature physics.
It was a tour de force, experimentally. Just brilliant work and incredibly courageous to pursue such a challenging path based on Li and Yang's radical suggestion.
And after Wu's result, did others quickly confirm it?
Oh, yes. Almost immediately, other labs confirmed parity violation in the decays of pions, muons, and other particles involving the weak force. The floodgates opened, the old assumption was gone.
So discovering parity violation wasn't the end of the story, was it? It immediately raised questions about other symmetries.
Absolutely. If P parity can fail, what about C, charge conjugation, and T, time reversal?
Charge conjugation being swapping particles for antiparticles.
Right. And actually, the Wu experiment also implicitly showed that charge conjugation symmetry was also violated in beta decay. So the weak force respects neither P nor C individually.
What about T, time reversal? Reversing the arrow of time.
That one's trickier. Whether the weak force violates time reversal invariance is still a very active area of research. The experiments are incredibly difficult.
But there's this thing called the CPT theorem you mentioned. How does that fit in?
Ah, the CPT theorem. It's a very fundamental result in quantum field theory. It basically says that if you perform all three operations together, swap particles for antiparticles, C, reflect in a mirror, P, and reverse time, T, the laws of physics must remain unchanged. CPT symmetry is believed to be exact.
Okay, so even if C is broken and P is broken, the combination CPT has to hold.
That's the idea. And it has big consequences. Since we know weak interactions violate both C and P, the CPT theorem implies something about T. Either T must also be violated in a specific related way to compensate, or T could still be conserved.
And if T is conserved by the weak force?
Then, interestingly, the CPT theorem implies that the combined operation CP swapping particles for antiparticles and reflecting in a mirror would still be a valid symmetry for the weak force, even though C and P individually are not.
Whoa. So a mirror image universe made of antimatter would behave the same as our universe made of matter, even though a mirror image universe made of matter wouldn't.
That's the fascinating implication if T is conserved. Yang notes this would even change how electric and magnetic fields transform under this combined CP operation compared to just P. It's a subtle but deep point.
It's also mentioned that the continuous space-time symmetries, like Lorentz invariance from special relativity, seem okay. They aren't broken by the weak force.
Right. That seems to be the case. The really fundamental symmetries related to the continuity of space and time appear robust. It's these discrete symmetries, C, P, and possibly T, that are violated by the weak force.
What about that other symmetry, isotopic spin? You said it was useful but different.
Yeah, isotopic spin isn't a space-time symmetry like parity. It's more like an internal property, grouping particles like protons and neutrons together. And it's only an approximate symmetry anyway, holds pretty well for the strong force, but both electromagnetism and the weak force violate it. Its deeper meaning is still kind of debated.
Okay, and one last point Yang makes is that all these different weak interactions, beta decay, muon decay, strange particle decay, they not only have similar strengths,
But the parity violation experiments reveal they also seem to violate P and C in a very similar, maybe even universal way.
which suggests there's something fundamentally common about how the weak force operates across all these different processes.
Exactly. It hints that this ability to distinguish left from right, P violation, and perhaps matter from antimatter, C violation, is an intrinsic feature of the weak force itself. And if T is also violated, then the weak force might be the only interaction that fundamentally distinguishes between past and future as well.
Okay, let's try to sum up this incredible journey. We started with symmetry as this bedrock principle in physics.
Foundational, yes. Dictating conservation laws, shaping theories from Newton to Einstein to quantum mechanics.
And parity, left-right symmetry, seemed like one of the most obvious, unshakable symmetries, assumed to be universally true.
Until the theta-tau puzzle threw a massive wrench in the works, showing two particles that looked identical in mass and lifetime, but had to be different according to parity conservation rules.
Which led the brilliant Li and Yang to question the unquestionable. Maybe parity wasn't always conserved, specifically in weak interactions.
A radical idea, born of frustration, that required checking assumptions everyone had overlooked.
And then came the crucial experiment by Wu and her team, cooling cobalt-60, aligning spins, and watching where the electrons went.
A technical masterpiece that definitively proved parity violation. Left and right are distinguished by the weak force.
This discovery didn't just solve the puzzle, it opened Pandora's box, forcing physicists to reevaluate CPT symmetries and revealing the weak force's unique role in the universe's asymmetries.
It fundamentally changed our view of the fundamental forces and the symmetries that govern them. A true revolution.
It really makes you think, doesn't it? If something as intuitively obvious as left-right symmetry could turn out to be conditional, not absolute. Well, what other obvious assumptions are we making in physics today that might one day be overturned?
That's the provocative thought, isn't it? It's a good reminder to always question, always test, and never take the apparent symmetries of the universe entirely for granted.
A perfect place to leave it. Thanks for exploring this deep dive with us.